Hi, so today we'll be reviewing the June 2023 Physics Regents. So starting off, number 1, which pair of quantities are both scalar quantities? So for this question, we need to know what a vector quantity and what a scalar quantity is. So a scalar quantity is something with no direction, okay? And a vector is the opposite. It's something with direction. So let's look at these choices. So 3 and 4 are out because they both have displacement. So displacement is a vector quantity, and let me explain this. Displacement is a vector because you need direction. Displacement is how far away you go from the origin point. So if you start the origin and you go up 5 meters, you're going 5 meters north. You're not just going 5 meters, you're going 5 meters north. That's very important. If you're just saying 5 meters, then that's your distance, and that's a scalar quantity, okay? Now we have 1 and 2 left. So speed is on both of them. Speed is a scalar quantity, that's correct. So it's either 1 with mass or 2 with momentum. So let me explain why momentum is a vector quantity. So momentum, the equation is P equals mv. V stands for velocity, so it's mass times velocity. The velocity is a vector quantity because if you're moving 5 meters per second, you have to move in a certain direction. You're going 5 meters per second down. If you drop a ball and the ball starts going downwards, it's going 5 meters per second south, right? So that's how we know that's incorrect. So that's why it's number 1. Because speed and mass are both scalar, while momentum, displacement, all of these things, those are all vectors. Number 2, in an attempt to get ketchup out of a bottle, a student takes off the cap, turns the bottle upside down, accelerates it downward, and then suddenly stops it. So let's picture this first. You're shaking a ketchup bottle, and you're shaking it downwards, and then out of nowhere you stop it. So after you stop it, ketchup is released from the open bottle because the ketchup doesn't stop moving when the bottle does. So even though the bottle stopped moving, the ketchup continues to stay down and it hits your plate. So the ketchup leaving the bottle illustrates 1, inertia. So the reason why it's illustrating inertia is because even though the bottle stopped moving, the mass of the ketchup continued downwards. It was already continuing that motion. It was already in that motion, and since the mass kept pulling it down, the ketchup left the bottle. And mass is inertia, that's why. Okay, so the inertia is what made it continue moving downwards. Number 3, the same net force is applied to object A and object B. The mass of B is 3 times greater than the mass of A. Compared to the acceleration of A, the acceleration of B is... So, net force. So our first thought here is F net equals ma. Just check your reference table. The equation's right there. So F net equals ma. We could just do substitution to figure this out. Let's substitute. So let's pretend F net is 6 for both A and B. Okay? So object A, object B, the F net is 6 for both of them. So since the mass of B is 3 times greater, let's pretend the base mass, the mass of A, is 1 kilogram. So the mass of B would be 3 kilograms. So we could plug this in, 3 times 2, 1 times 6. So these are our masses, 1 and 3 is our mass, 6 and 2 are our accelerations. So compared to the acceleration of A, the acceleration of B is 1/3 as great, because 2 is 1/3 of 6. Number 4, what is the mass equivalent of 3 times 37 to 10 to the negative 9 times 10 to the negative 19th joule? So once we see joule, we're immediately going to think of energy. We could look through our reference table and look through all the energy equations, and since we're looking for our mass here, we need something with mass and energy, and that will be E equals mc squared, right? Einstein's equation. So we have our E. It's 3.37 times 10 to the negative 19th joule, and that's going to equal mass, what we're looking for, times c, our constant. That's the speed of light, and that will be 3 times 10 to the 8th squared. So when you do the math, you're going to get 2. 3.74 times 10 to the negative 36. 5. Which object is in equilibrium? So remember, equilibrium is when your F net is 0, okay? So it's when everything cancels each other out and you're completely balanced, you know? everything is looking for balance in life, and that's equilibrium. For example, if this box is being pushed 5 meters here and 5 meters here, it's in equilibrium. So the answer here is going to be 3 because that's at constant speed, okay? Constant is our key word. This is our very important key word for equilibrium. If something is at constant speed, it's at equilibrium. The F net is 0, okay? Because this is moving at constant speed, this box here, and the F net is 0. Because F net is just our total forces, and this 5 meters over here and this 5 meters over here, these cancel each other out. They cancel out. Number 6, a race car travels around a flat circular track at constant speed. The net force on the car acts. So, circular, this is going to be our key word. When we think of something circular, we should immediately think of centripetal force, okay? So, this is kind of like a memorization question. You just have to remember how an object in centripetal force acts. Always remember, it's going to be perpendicular, not parallel. Never parallel, okay? So when the race car is moving around that circular track, the force, the centripetal force, will be acting perpendicular to the car, right? And when it's acting perpendicular, the force of the car is trying to push it towards the center. It's going towards the center, not away. Never away. No. So it's going to be number 1. Number 7. An object is traveling in a horizontal circular path at constant speed. If the radius of the path were doubled while the speed remained constant, the centripetal acceleration would be... So remember what we did for number 3? We're just going to do the same thing here. We're going to plug it in. So centripetal acceleration. Our equation for this is going to be AC equals V squared over R. So our AC, we have to see what the relationship here is. So let's pretend our V is 2, our velocity is 2, and our radius is also 2. So AC equals V squared, 2 squared, that's just 4, over 2. So AC equals 2, right? So let's do our other AC. So that's AC1, that's our basic one. So now we have to see if the radius were doubled. So 2 times 2, that's 4. So we have our V squared, that's 4, and our doubled radius, which is 4. So our new AC is 1. Let's compare these two. So if the speed remained constant, but the radius is doubled, that means that our AC, our centripetal acceleration, would be halved. 8. A 600 Newton student pushes on a vertical wall for 20 seconds with a constant force having a magnitude of 100 newtons. What is the magnitude of the force that the wall exerts on the student? So this is just Newton's law. Don't think about all the different numbers here. They're trying to trick you. Just remember that says the student is pushing the wall with a force of 100 newtons. Whenever you push something, it's going to push back, okay? So if I'm exerting a force of 100 newtons onto this wall, the wall is going to exert back a force of 100 newtons on me, okay? For example, if I have a baseball bat, I'm hitting the ball exerts 100 newtons onto the bat is going to exert 100 newtons onto the ball, okay? Number 9. An unbalanced force of 20 newtons is applied to a mass of 1 times 10 to the third kilograms. After 10 seconds, the momentum of the mass will have changed by... So, the momentum of the mass, the change of that is change in momentum. And if you look at the reference table, we have our equation. Change of momentum equals F net times T. So, we have our F net, it's right here, 20 newtons. And we multiply that by 10 seconds. That's going to be equal to 200, which is just number 1. 2 times 10 to the second. Number 10. To lift a heavy block off the floor, a student pulls the force on a rope that passes over a pulley as shown in the diagram below. You see it right there. Which pair of vectors represents the perpendicular components of the force that the student exerts on the rope? So, this is our F. It says it right here. It has it right there. Okay? So this is our resultant. That's the result of 2 different forces pulling on it. and we have to figure out what those forces are. So we could just draw it out. What's the resultant? It's going to look something like that. Okay, and which one looks the most similar? That's 2. 11. Which graph best represents the relationship between the mass of an object and its distance from Earth's surface? So this is very important. This question, a very important piece of information. And that's going to be mass is always the same. You have to remember that. For this question, for general information, you should always remember that. Mass will always stay the same. Your weight can change, but your mass is always the same. So no matter the distance, the mass will stay the same. 1. Like if you're on the moon, your weight is going to be different. You're going to be lighter, but your mass will still be the same, okay? 12. A compass is placed near a strong bar magnet as represented in the diagram below. Which diagram best represents the direction of the compass needle? So, remember, for direction, for compasses, magnets, the opposite is always what attracts. So, for example, north and north are going to repel each other, but south and south are also going to repel each other. North and south is what attracts. So, north can't be here. This is not allowed because north and north, no, they repel each other. But south and north are going to attract each other. That's okay. So, the compass is going to be north on the left, south on the right, which is 3. 13. As Earth orbits the sun in its elliptical orbit, the gravitational force between the sun and the Earth is always attractive. It will always be attractive. Just remember, our Earth is in orbit because the sun and the Earth are attracted to each other. 14. Which unit is used to measure the work per unit charge required to move a charge in an electric field? So that is going to be volts. So don't get scared by this question. Just look at the reference table. We can see here that work over charge, which is work over Q, that's equal to volts. Okay? That's on the reference table. 15. The diagram below shows a negatively charged sphere and a point P located within the electric field produced by the charge on the sphere. So the charge on the sphere is negative. So remember, negative goes inwards. So the arrows are going to be drawn like this. They're going in. You could just remember this as a little trick, like negative people are self-centered. So it's like, oh, everything should be about me. The arrows are going into me. Well, positive people, positive charge, it's going outwards. Because positive people always have something nice to give. Right? So point P is going to be going like this. Because the negative sphere will be attracting inwards. So point P is going to go in and it's going to hit D. It's going through that direction. 16. 2-point charges, charge 1 and charge 2, are initially a distance D apart. Which change will cause the greatest increase in the electrostatic force between the 2-point charges, charge 1 and charge 2? So we could just plug in for this one. So remember, our electrostatic force equation is Fe equals K times Q1, Q2 over R squared. So we have to see the change, what would bring the greatest increase in the electrostatic force. So Fe, we could just plug some stuff in. So for our purposes here, I'm not gonna use Q. I'm not gonna use K. I'm just gonna pretend that K doesn't exist because it's gonna stay the same for both of them. None of these answer choices have anything different in K. It's constant. So Q1, I'm gonna say Q1 is equal to 4. And Q2 is also equal to 4. And our radius is equal to 2. So Fe equals Q1 times Q2. So 4 times 4, that's 16. And that's going to be over 2 squared, which is just 4. So our Fe for this one is going to be 4. So let's make a big change, an increase. So if I double D, that's going to make things smaller. Remember? Because of this inverse relationship right here. So if R squared, the radius, gets bigger, then the force here has to get smaller. But I want there to be an increase. So in order to make Fe bigger, this has to get smaller. So let's try to have D. So D is initially 2. Let's make it 1. So 4 times 4, once again, are charges. It's going to be 16 over, instead of 2 squared is 4, it's going to be 1 squared is 1. That's 16. So see how huge that change is? It's 4 times as big as it once was. So that means we have to have D in order to make the biggest increase. The diagram below represents 2 identical conducting spheres. Which statement could be the correct explanation for the charge distribution on the spheres? So, everything here is talking about something between sphere A and sphere B for the first 2 choices. So let's look at that first. So let's focus on this. On the right side of A, it's positive. On the left side of B, it's also positive. Usually it'd be the opposite. So something has to be in between here that's making it attract. That's going to be negative. Remember, positive and negative attract each other, while positive and positive or negative and negative repel each other. So if there was nothing in between here, this wouldn't make sense, because the 2 positives over here, positive in A and positive in B, they're both going towards each other. That's not right. So a negative has to be in between for that. And that would also explain why the negatives over here are kind of like running away, right? So that means the choice would be B. 2. 18. The diagram below represents a circuit containing a battery, 2 operating lamps, A and B, and 4 closed switches, S1, S2, S3, and S4. Which switch, when opened, causes both lamps to turn off? So that's going to be switch 1. This is switch 1 because switch 1 has full access to everything, okay? So it's right where the battery is. These 3 switches, they only control certain parts, while this switch, switch number 1, it controls the entire thing. If you turn it off, the whole lamp shuts off. What is the resistance of a 100-watt bulb when operating a potential difference of 120 volts? So, 100-watt bulb. So when it says watt, that's when you think of power. So we could look through all the equations for electricity, and we see power equals V squared over R. So our power is 100 watts equals V squared, 120 squared over R. And when you do the math, R equals 144 ohms. 20. The interaction that is most responsible for binding 3 quarks together in a proton is the strong force. So remember, it's strong force because this is like the most powerful thing ever. You're binding together these 3 tiny like molecules. You need a strong force in order to do that. It's not going to be electromagnetic. Why would it be weak, and why would it be gravitational? So it's obviously strong force. 21. One example of a force doing work is the force exerted by what? So let's take a look. Remember, work, the equation for work is work equals force times direction. So you have to be moving in order to do some type of work. So 1. Earth on a high diver falling toward a pool from a platform above. So this is gravity having some type of force on this person. This person is diving down into a pool. So they are moving. So let's keep that in mind. So this is a good option. Let's look at number 2 though. A hook on an engine held stationary above a car. So we immediately know this is wrong because of the word stationary. That means it's not moving at all. If it's not moving, there's no type of direction or displacement. So it's no work. 3. A frictionless horizontal air hockey table on a puck moving across the table at constant velocity. So constant velocity. Remember, work equals force times distance. There's no force happening in number 3 because the net force, the F net, equals 0. Remember, if it's constant velocity, it's 0. So that means that there's no work happening there. Number 4, a weightlifter on a barbell, he holds motionless over his head. Motionless. Nothing's happening, no moving. That means it's not 4 either, it's number 1. 22. A ball falls freely from a rooftop to the street below. The ball starts from rest with 20 joules of gravitational potential energy with respect to the street. The total mechanical energy of the ball just before it hits the street is, let's see. So, mechanical energy is the sum of kinetic and potential energy. Remember that. So mechanical equals PE, potential energy, plus KE, kinetic energy. So when it starts from rest, the ball is up here. It has 20 joules of gravitational potential energy. 20 equals PE. And it should have 0 joules of kinetic energy. And that's because when it's at the very top and it's not moving, it has so much energy built up. But kinetic energy needs some type of motion, because remember the equations. KE equals 1/2 times mass times velocity squared. There's no velocity happening, which means KE is 0. But when it reaches the bottom, it's at the bottom here, the things are reversed. There is 20 joules of kinetic energy while there's 0 joules of potential energy. And that's because the ball is moving as fast as it can now. The kinetic energy is at its max while the potential energy is all used up. It's turned into kinetic energy. So there's 0 PE now. So the mechanical energy, though, it's just PE plus KE. So in all these situations, no matter what, it adds up to be 20 because 20 plus 0 is 20. So 22 is 4. 23. Which statement describes the gravitational potential energy, PE, the KE, and Q of a wooden crate as it is pushed across a level classroom floor at constant speed? So this is going to be 4, and let me explain why. When you're pushing something across a level floor, the KE and PE are both going to stay the same. It's a level floor, which means the height is consistently the same, and it's going at constant speed. The equation for PE, potential energy, is mass times gravity times height. So if the height stays the same, and the mass stays the same, and gravity is a constant, everything's going to stay the same. The PE will not change. And the equation for KE, kinetic energy, is 1/2 times mass times velocity squared. Our mass, once again, doesn't change, and if we're going at constant speed, the velocity doesn't change either, which means KE is going to stay the same. But when we're moving the crate, as we push the crate, thermal energy is going to build up. The Q, the thermal energy, is going to increase. Just pretend like you're moving something across the floor and you're moving it for a while. If you touch the bottom of that object, it's going to be like a little bit warm after you do it for such a long time. That's because the thermal energy increases. That's why it's 4. 24. The oscillation of electrons up and down a metal antenna produces waves. These waves are... So let's look at these choices. So in all these choices is asking you whether it's mechanical or electromagnetic. So we can obviously tell this is not a mechanical wave because it's the oscillation of electrons up and down. Electrons. Electrons equals electromagnetic. Just know that. And it's also kind of like common sense because electrons, electromagnetic, you could kind of guess the relationship. But now we have to figure out if it's transverse or longitudinal. So something you have to remember is how a transverse or longitudinal wave moves. So a transverse wave is a wave that moves up and down. You have to remember that. While, different color here, a longitudinal wave is a wave that moves left and right. So the oscillation of electrons up and down, that is a transverse wave. And this might be a little bit hard to remember, but just try your best. That transverse waves are up and down, while longitudinal are left and right. 25. The diagram below shows an incident light ray reflecting from a plane mirror. So when we do anything with reflections or incidents, remember, always draw the normal line. 1 second, draw the normal line. So the normal line is just going to go straight through. And since this whole angle is 84, we can just divide that by 2 because it's getting split in half. So 84 divided by 2 is 42. So 42 here, 42 here. That just means our angle of reflection, our incident angle, and our reflected angle are both 42. 26. A characteristic common to both sound waves and X-rays is that they both, let's see. So, number 1, they travel fastest in a vacuum. I'm not sure about that, but we can come back and visit it if there's no better option. Number 2, cause particles to vibrate in a direction parallel to the wave's direction of motion. So, parallel. What we said up here about this whole transverse, longitudinal, left and right thing, it also applies to this. So, a longitudinal wave, the one that goes left and right, that's a parallel wave. So, I'm just going to say longe, that equals left and right, which also equals parallel. Remember that. While transverse is up and down is perpendicular, right? And some information that you need to remember is that sound waves are longitudinal. So a sound wave is longitudinal, that's parallel. So that part is correct. But an X-ray is not parallel. An X-ray is a transverse wave, which means it's perpendicular. So since the sound wave is parallel, but the X-ray is perpendicular, that means 2 cannot be correct. 3, they transmit energy without transmitting matter. So number 3 is correct because they transmit energy without transmitting matter. For example, like a sound wave, does that have any type of matter? Does it have any type of mass? No. It's just a wave. It has no type of matter to transfer anyways. 27. The diagram below represents a wave moving to the right through a rope. Point P in the rope is moving toward the, let's see. So this question is something that I used to get wrong all the time, but then I learned a little trick. And this might sound stupid, but trust me. You always look at the opposite direction. And you might be wondering why. So you look at the opposite direction because you see this wave is moving to the right? This arrow here. So instead, look to the left of the point. So our point is here, look to the left. What's happening on the left? It's going up. It's moving up. So it's moving to the top of the page. And you could check this, and this is correct. It might seem weird, but trust me, you have to look at the opposite direction. 28. What is the wavelength of a 300 hertz sound wave in air at STP? So let's look at our reference tables. So the speed of sound in air at STP is 3.31 times 10 to the second meters per second. So now that we know that, we could just use another equation in our reference table. So velocity equals frequency times lambda. So now we have our velocity. It's 3.31 times 10 to the second meters per second. Because remember, this is 3.31. That equals frequency. And we have our frequency right here, 300. And that's times lambda. And after you finish doing the math, you're going to get 1.1 meters. 29. In the diagram below, a remote control is aimed at a television. When the signal from the remote reaches the sensor on the television, the signal will most likely be 2, partially absorbed and partially reflected. So this isn't really talked about in many physics lessons. It's more sort of common sense. So when you have your remote and you're trying to turn something on the TV, the signal will reach the TV, but not the whole thing is going to be absorbed. Part of it is going to be reflected up to like a satellite or something. So remember, it's always just partially absorbed. 30. Compared to waves of blue light traveling in a vacuum, waves of red light traveling in a vacuum have. So let's just open up our reference tables and look at the electromagnetic spectrum. So we could see here that blue light has a higher frequency. It has a frequency of 6.59 times 10 to the 14th, while red light has a frequency of 3.84 times 10 to the 14th. So compared to blue light, red light has a lower frequency, but it has the same speed because it's in the same vacuum. So everything in the same vacuum is pretty much at the same speed. 31. Earthquakes often cause buildings between 12 and 40 stories high to vibrate at an amplitude high enough to be destructive. Buildings are often designed to absorb this vibrational energy that might cause them to vibrate at their natural frequency. This tendency for an earthquake to cause a building to vibrate at a large amplitude is an example of 1. Resonance. So the reason why it's resonance is because when a question mentions vibrations, immediately think it's resonance because it's always resonance. Resonance is the vibration, and look at how many times this question says vibrate. The answer is resonance. 32. During the radioactive decay of a uranium-238 atom, a thorium-234 atom, and an alpha particle are produced. During this process, there is a conservation of C, both charge and mass energy. This is just a law. There's always conservation of mass, energy, and charge. Remember that. It's always conserved. 33. An antiproton has a charge of, so it's an antiproton. Anti just means it's the opposite of that thing. So a proton has a charge of +1, right? So if it's anti, it's going to be negative. So it's going to be negative 1e. Also, just think of it like a proton. The opposite of a proton is an electron. What's the charge of an electron? That's negative 1e. Easy. Two pulses approach each other in the same medium. Which pair of pulses will result in the largest magnitude displacement of the medium as the pulses pass through each other? So number 1, that's just going to cancel out. See, these two, they're going at opposite directions, but they're like the same height. So it's just going to cancel out and become like a straight line like this. So it's not 1. So 2, they're going at the same direction. So once they meet up in the middle, it's going to become something like this. It's going to be huge. The same thing with 3. It's not the same. You could tell this is a little bit bigger than this one, like the depth. But they're going at opposite directions. So that means that when it meets up, it's just going to end up being like this. So that's tiny. No. And then 4, it's going at the same direction, and they're both moderate heights. So it's going to be something like this. But 2 is obviously the biggest one because look at this. This is way bigger than these two are. 35. Two waves of the same wavelength interfere to form a standing wave pattern as represented in the diagram below. Which point on the diagram represents a node? So let's just look at where the nodes and the antinodes are. Also, we could just take out B because B isn't even where anything lies. So B is gone. And it's also not A or C because A and C are both in like the same type of point. So we could just deduce that it's not A or C and that's D. That's correct. But let me explain why. So nodes are placed here. Node, 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 node. Well, antinodes are straight in the middle like this. There's always one more node than there is antinodes. So for example, here there are 5 nodes and there are 4 antinodes. So that's how you know that's correct. And also see here, D is where the node is. Now we're on to part B. So 36. A round dinner table has a diameter closest to, this is just like a type of estimation question. So 2 times 10 to the negative 1. That's around 0.2 meters, which is a Yeah, that's a decent dinner plate size. 37. Several springs are lying on frictionless tabletops with one end attached to a wall and a variable force F applied to the free end of each spring. The springs have different spring constants, K. The diagram below shows the setup for one of the springs. The elongation of the springs produced by force F depends on, let's see. So, we could use the equation for the force of a spring. So, Fx equals Kx, which is just force of a spring equals spring constant times the elongation of a spring. So, if we want to see what the force F depends on based on the elongation of the spring, we have to get the x, the elongation of the spring by itself. So we could just make a new equation here by just dividing, and we'll get x equals Fs over K. So an inverse relationship is when something goes up and the other thing goes down. So for example, if we increase K here, then that means our x is going to go down. So K, our spring constant, has an inverse relationship. So let's look at this. Inverse on K for number 4, that's right. Inverse on F, but direct on K for number 3, that's wrong. Directly on both F and K, nope. Directly on F and inversely on K, maybe. So now let's look at the other relationship. Let's see if it's directly on F. So if we increase F, that means X will also increase. So that means there is a direct relationship for the force and the spring elongation. So that means the answer is 2. There is a direct relationship for F, there's a direct relationship for F and an inverse relationship for K. 38. The table below shows the weight of 4 athletes, A, B, C, and D, and the time required for each athlete to run from the base of a hill to its top. Which athlete ran up the hill with the greatest average power? So, the equation for power is power equals work over time, or force times distance over time. So, let's take a look here. To figure out which athlete ran up the hill with the greatest average power, all you have to do is divide the weight and the time, because they all ran the same distance, so that's negligible, because it says they all ran from the base of the hill to its top. So all you have to do is divide each of them and figure out which one has the greatest power, biggest number, and that's going to be C. A copper wire carries 2.8 amperes of current. The total amount of charge that passes a point in the wire in 1.3 milliseconds is... So let's see here. Let's look at the different electricity equations. So the one that's going to fit this question is I equals Q over T. So we have our I. That's going to be 2.8 amperes of current. We don't have the total amount of charge. That's what we're looking for. So 2.8 equals Q over 1.3 milliseconds, which is also 0.0013 seconds. So once we do that, we solve for Q, and then we're going to get Q equals 3.6 times 10 to the negative 3 coulombs. 40. The diagram below represents 4 solid copper wire segments at 20 degrees Celsius with different lengths, L, and cross-sectional areas, A. Which 2 segments have the same resistance? So, to figure this out, we could take the equation which has all these different components. And that equation is going to be resistance equals resistivity times length over cross-sectional area. So the resistivity of all of these segments is going to be the same because they're all made out of copper. So this is negligible. Now all we have to do is divide the length and the cross-sectional area to get all of these. So the resistance of this is 1, this is 0.5, this is 2, and this is 1. So that means A and D are the same. They have the same resistance. 41. In substance X, a ray of light with a frequency of 5.09 times 10 to the 14th hertz has a speed of 2.04 times 10 to the 8th meters per second. Substance X could be So to find substance X, we need to find out what its index of refraction is. So if you look on the reference table, the equation we should be using is N equals C over V. Since we already have C, it's the speed of light, which is a constant, 3 times 10 to the 8th, and we have velocity, which they just gave here. So N equals 3 times 10 to the 8th over 2.04 times 10 to the 8th. So when you divide these two, that's how you get N, and N in this case is going to be 1.47. And if you look on the reference table one more time, if you look at all the index of refractions, 1.47 is equal to glycerol. Now, 42. Which could not be the charge on a particle? So when it says the charge on a particle and it gives you all these different numbers, you have to figure out what an elementary charge is. That is also just like the simplest number for a charge. And if you look on the reference table, an elementary charge equals 1.6 times 10 to the negative 19th. So we have to find out which one of these cannot be this. So if you just multiply 1.6 times 10 to the negative 19th by different numbers, these are all just different types. So 1.6 times 10 to the negative 19th times 2, that's 3.2 times 10 to the negative 19th. Or I'm just going to refer to it without the 10 to the negative 19ths. So 1.6 times 2, that's 3.2. So that can be the charge on a particle. So it's not right, because it can be the charge. This is like two charges. So 1.6 times 3, that's going to be 4.8. So that's 3 charges. And then 1.6 times 4, that's 6.4. So that's going to be 4 charges. So these are all 1, 3, and 4. They're all possible charges. But 2 is the correct answer, because 2 cannot be the charge on a particle, because it is not a multiple of 1.6 times 10 to the negative 19th. 43. Which graph best represents the relationship between photon energy, E photon, and wavelength? So let's look at the reference table to find this formula. The formula for this is going to be E photon equals hc over lambda. We needed to find a formula that had both E photon and wavelength. This is our formula. So now we have to see the relationship between them. So the relationship between E photon and the wavelength is a inverse relationship, which means if lambda, or the wavelength, increases, then E photon has to decrease. And if E photon increases, then the wavelength has to decrease. So in this case, as the wavelength increases, E photon decreases. So that means 43 is answer 4. 44. Light travels from air into another medium with an index of refraction of n. The light has a wavelength of 6 times 10 to the negative 7th meter in the new medium. Which expression represents the wavelength of this light in air? So let's write down all the information we know. So we know that light is initially in the air. So the index of refraction for air is just 1, right? Let's check our reference table, and that's correct. So our N1 is going to be air, which equals 1. Our N2, we don't know that yet. It's a mystery. Then we have our wavelength. Our first wavelength, we're not sure about that. But we know our second wavelength after it's in the new medium. That's 6 times 10 to the negative 7th meter, right? Let's just take this. I'm going to make it tiny. I'm going to put this in this corner. Now, we could look back on our reference table to find our formula. So if you look in the wave section of your reference table, you could see N2 over N1 equals V1 over V2 equals lambda 1 over lambda 2. So that's what we're going to use. N2 over N1 equals lambda 1 over lambda 2, or wavelength 1 over wavelength 2. And we just plug it in. So we have N2 over 1 equals wavelength 1 over 6 times 10 to the negative 7th. And once we do a little bit of math here, we just cross multiply, and we get 6 times 10 to the negative 7th times n equals lambda 1. So which expression represents the wavelength of this light in air? That's going to be answer choice 1. 45. If 80 joules of electrical energy is dissipated by a 10 ohm resistor in 2 seconds, the current in the resistor is... So, electrical energy. This just means work. You could look at the reference table. It's going to have all the different definitions of the symbols, and it will also have the different equations. So the equation we're using for this one is going to be work, or electrical energy, is current squared times resistance times time. So the work here is 80 joules, which equals current squared, which is what we're trying to find, times resistance is 10, and time is 2. So after you do all that math, you're going to get I squared equals 4, so I is 2. That's answer choice 2. 46. Which wave has a period that's twice that of wave W? So, remember, the period is basically the time it takes for one wave to pass. So, wave W. So, A, B, C, D, E. So, this is one wave. This is where one wave happens. So, for wave A, B, C, D, E, this is where one wave happens. A, B, C, D, E, one wave. A, B, C, D, E, one wave. A, B, C, D, E, one wave. So which wave has a period that's twice that of wave W? That is going to be wave C. You can see that's the only one that takes longer than wave W. Which wave is always 180 degrees out of phase with wave W? So when it's asking you if it's 180 degrees out of phase, that just means when wave W is at point B, what's 180 of that? So that's going to be wave A, because as you see, they're like inverses of each other. They're absolute opposites of each other. See that? They're opposites of each other. When this is going here, this is going the exact opposite way. They're even, just flipped around. So 47 is A. 48. Which graph best represents the relationship between acceleration and time for a freely falling object as the object falls near the surface of Earth? So the acceleration of a freely falling object, acceleration is always 9.81 meters per second squared. That is a constant. So nothing changes. No matter the time, nothing changes. There is no change. Acceleration is always 9.81 meters per second squared. Now 49. The diagram below represents the forces acting on a skydiver with his parachute. The total mass of the skydiver with his parachute is 85 kilograms. So this guy's 85 kilograms. If the magnitude of the gravitational force is 834 newtons, and the magnitude of the force of air friction is 652 newtons, the acceleration of the skydiver at the time shown is... So to figure this out, we need to find out what the total force is. So what is F net? So we could just figure this out by seeing the diagram and seeing all the numbers we have. So we know that the gravitational force is 834 newtons. So it's going down 834 newtons. But there's a frictional force. So there's another force applied that's making it go up 652 newtons. But it kind of just cancels out. So it's basically 834 newtons plus negative 652 newtons, or 834 minus 652. And that's just going to give you a value of 182 newtons. So the full force, the total F net force, is 182 newtons going south. It's going downwards. Now we could use F net equals ma in order to get the acceleration, because that's what we're trying to find. We already know the mass, so just plug in 182 newtons equals 85 times the acceleration. So our acceleration is 2.14 meters per second squared, and obviously since the gravitational force, the whole force actually, is going south, this acceleration is going south too. 50. A 15-gram air hockey puck sliding on a horizontal surface at a velocity of 7 meters per second north collides with a 15-gram air hockey puck traveling at a velocity of 8 meters per second south. The momentum of the system of pucks after the collision is... So to figure this out, we could just draw a diagram first. So there is a puck going 7 meters per second north and one going 8 meters per second south. So obviously we know that the 8 is going to overpower the 7, and the system of pucks is going to end up moving southward. So we can eliminate 1 and 2, 1 and 3, which both say north, because that's not right. So it's either 2 or 4. Now we know that there is a conservation of momentum, which means that these two pucks together, it's going to end up being the same thing as they once were. So, the momentum of the first puck is P equals mv. That's our equation. So the first one, both of them are 15 grams, which is 0.015 kilograms. So it's 0.015 times 7. The other one is 0.015 times 8. So this equals 0.105, 0.12. And they kind of just cancel out. So 0.12 minus 0.105, that just equals 0.015. And that will be going southward. So that's how we know it's number 2. So, if you guys need any help in physics, I'm going to keep doing these reviews, and I'm going to post the one for all of these short response questions in a day or two. Have a nice day, and do good in your study.